Hi everyone, so my name is Teodora Kirova. I was seconding from South Africa on the Fotonika project. Then I worked for 2 years on that project, and now I've been elected leading researcher at the Institute of Atomic Physics and Spectroscopy. So Fotonika project has contributed to my professional development. So during my work, I was cooperating with people from the Laser Center, the St. Petersburg State University, Kaust, as Aigars said, and people from Novosibirsk. So I'll be talking about theoretical work on creation of multiple trace states in hyperfine levels of sodium. Aigars already talked about it, but let me just remind you about what are trace states. These are mixed states created because of light-matter interaction. So if you have two atomic or molecular states coupled by a laser, the result is a mixture between those two states, and these are called trace states, and the mixing angle between them depends on the Rabi frequency of the laser and also on the tuning. How can we observe these states in reality? We have to take the coupled system and then couple it with another weak laser to ground state, and then scanning this weak laser we can observe the population from the trace states, and you can see peaks in the fluorescence spectrum, which are the so-called out and down peaks. And their ratio depends also on the tuning of the laser and the Rabi frequency. Now we want to see the alpha-mass effect in more complicated systems than just two-level systems. So atomic sodium with its hyperfine structure gives us this opportunity to include more levels in our system by including the Zeeman and hyperfine levels. What should happen in this case? Usually, when you look at these systems, you have to take into account the so-called Morris short transformation, which tells you that if you have a multiple system coupled by laser, the result should be creation of bright and dark states. So depending on the number of states in the upper and lower level which are coupled by the laser, you should have the minimum of those states should be created bright states, and the difference between the number of those states should be the created dark states. And as Aigars told you, dark states are the ones which do not interact with the system, so you should see no fluorescence from them, and the bright states should be the ones that you see as peaks in the fluorescence spectrum. To check this creation of dark and bright states in our sodium system, we took this excitation scheme, which later on we modified for different intermediate and final levels. In this case, we took into account all the hyperfine splittings and also all the fine hyperfine and Zeeman sublevels. And the transition dipole moments, which depend on all the quantum numbers, they also had to be included in our models. So we developed two models, one of them based on Schrodinger's equation, where you have the wave function, which is decomposed by the basic states of the system, and then in the Hamiltonian you have the atomic Hamiltonian, which is diagonal in the atomic states, and then you have the interaction between the laser fields and the atomic transition dipole moments. Once you have your wave function and your Hamiltonian, you can solve Schrodinger's equation. And we have written our codes for each separate excitation scheme, and we observe the fluorescence from the upper level. That's our first model. The second model was developed by our colleagues in St. Petersburg. is based on the so-called split propagation technique. It's a little bit more complicated. In that case, you have to divide the Hamiltonian by different parts, which includes coupling of the ground state, coupling of the ground and intermediate state, coupling of intermediate and final state, and also the key processes. And after that, once having the Hamiltonian, we can apply the evolution operator to the density, to this matrix, and then you can solve for the density matrix operator and observe the fluorescence again from the upper state. What are the results of those two models? First, we took the excitation scheme that I showed you on the first slide. It is the most simple one, or that's what we thought, because if you look at the couple system, the number of states in the intermediate and final state is the same. So you should not observe any dark states in this case according to the Morris short transformation. You should just have bright states. And so we performed these simulations for different Rabi frequencies of the coupling field. And we see that at first we see some peaks which are due to the two-photon interaction. After that, we start observing the Arturs effect because the coupling field is growing, and we see that the number of peaks increases until we have full resolution of all the sublevels. And indeed, in this case, we just see bright peaks, which correspond to different Zeeman sublevels in the excitation scheme. After that, we looked at another system by replacing the upper state with a more complicated state, which has a bigger J number, and repeated the same simulations. Again, we see, due to Arturs effect, creation of some peaks, but in this case, they are actually their number is less than in the previous case, and that is because we have a lot of dark states created, because the number of states in the intermediate and final levels is different, so you should have dark states, which when you look at this curve of the energies of the dry states versus the coupling Rabi frequency, the dark states are the one that does not change the energies with the when the Arturs happens, and because they're not coupled into the system. Here is a slide that shows the matching between the two models. So you can see that two models look, the results of the two models look pretty much the same. So we are actually confident that our theoretical predictions are correct. Then we started investigating more complicated systems, where we started also adding more levels in the intermediate state. So this is 3p3 half, 3p3 half. In this case, our simulation showed that actually first you have your resonance, then you start increasing the number of peaks, but then somehow the peaks on the side of your spectrum actually disappear, and only the ones in the middle stay visible. When we changed the final state to 3D 5 halves, we saw a similar picture. So first increasing of number of levels, and then the ones on the inside of the spectrum this time disappeared, and the outside ones stayed. So we started looking more into this situation. Our colleagues from St. Petersburg calculated the energies of the trace states versus the coupling field Rabi frequencies, and then they drew all the possible couplings between the ground excited and final states, between all the F and M sub F sublevels, and for each, and they have done this for each different Zeeman sublevel. So for the 3p3 half, for the 5 half, we have seen, we have done more detailed simulations, and indeed, you see that the states that are created according to the Auzins effect eventually disappear, and this actually turned out to be bright states that disappear and not dark states, which is interesting. And the second interesting thing is that if you look at the excitation from F1 and F2 in the ground state, which is the brown and the black and the brown dash curves, they're actually complementary to each other, from which our colleagues in St. Petersburg found out that there will be more interesting applications, like polaritons, the opportunity to create a polariton. We repeated the simulations for the same excitation scheme at a different detuning of the coupling field. Again, for ground excitation coming from ground state F1 and F2. And for that excitation, for that detuning, is actually better seen how the peaks from the excitation from ground state F equals 1, which are really strong here, eventually they become smaller and smaller and disappear. So this was the disappearance of bright peaks. Now we went back to the excitation scheme with 5s 1 half and intermediate level 3p3 half, and we actually saw another effect, which is due to the destructive interference between different pathways when you look at all possible couplings and all the possible ways to excite the upper state. Due to the destructive interference, a lot of these peaks actually disappear, and they give us the opportunity to apply an artificial selection rule of f equals 0, which means that if you start from ground state 1, you end up in the final state f equals 1, and if you start from ground state 2, then you end up only in final state 2. And then we ask ourselves, is that the only system where you can observe these selection rules, the modified selection rules? And we went back to our very first excitation scheme, where no dark states are supposed to be created due to the Morris-Short transformation, and which was really simple, and we saw all the levels resolved. And we started actually reducing the hyperfine splitting of the intermediate level, and we saw that when it becomes really small compared to the right frequencies that we apply, all this rich structure of all the levels that we had actually disappears, and again we see only 2 peaks, as in the case of the modified selection rules. So we think that also in this case, at the right conditions for the hyperfine structure splitting, we can also observe the modified selection rules. And so, in conclusion, we have studied different ladder excitation schemes in sodium. We saw the creation of bright and dark states under different conditions. In the simplest case, where all the levels in the intermediate and final states are the same, we saw only bright state and no dark states. As we changed the number of states in the upper level, we saw the creation of dark states. In some of the cases, we saw an interesting situation where actually the bright states were the ones that disappear, and not the dark ones. And also, we saw independent excitation from the 2 ground states, which opens opportunity for creation of the component polaritons. In the specific case of 3p3 half, 5s 1 half, we saw the creation of artificial selection rule due to destructive interference between all the pathways. And when we went back to this very simple case, where we were seeing only bright states, and started playing with the value of the Hyperfine structure constant, we saw that again we see this selection rule delta F equals 1. And so this project has been supported by the Photonika funding, and also some smaller projects like exchange project between all the European and third world countries, and also Lithuanian, Taiwanese, and Latvian grants. Thank you.
Thank you. Are there some questions or comments?
Just a technical question, because we also use oblique equations for simulations. How many atomic states did you have in your biggest models there?
I cannot tell you exactly because we see we study different combinations of states here and here, but basically you have all the fine structure, the hyperfine structure, and then on top of it the Cinins levels. So it's quite a lot.
So how many? Like 10 or 50, 100 or?
Well, for each F you have to F plus 1 m sub f's, so you can calculate. So.
What is the simulation?
No, I'm just asking because the difficulty of numerical solving these equations is scaled as a square of the number of levels which you take into account. So.
Yeah, well, there is quite a bit of states. I cannot count them right now, but yeah, for each level we have the m sub x.
Okay, good.
I'm sorry, what was your question?
Your simulation tool.
Yes, the one that I worked on, the Schrodinger's equation, I wrote the equations in Mathematica. We saw them in Mathematica. For this one, I think my colleagues used maybe C++, I'm not sure, because these are not equations.
Your own environment.
Yeah.
Then we don't define the number of states?
No, we define them, but they serve, they're different for our excitation schemes. So.
Okay. Thank you.